exponents. And after we introduce these topics, we'll work through some examples. So let's begin with a definition. We say that a set is a well-defined collection of objects which are called elements of the set. So a set is a collection, and the objects in the collection are called elements. So we want to know set and elements. And when we use the word well-defined here in this definition, we mean that it should be possible to determine whether an object belongs to the set and hence is an element of the set, or doesn't belong to the set, and there shouldn't be any question about whether or not it belongs to the set. It should be clear. So here are some examples of sets, and we'll see these examples throughout our course in college algebra. In particular, sets are going to be very important when we start solving equations and we talk about the set of solutions of an equation. So the first set that we'll want to know is the empty set. So this is the set with no elements. So an empty collection, a collection with no members. And we use the Greek letter phi, as you can see here, the Greek letter phi we use to denote the empty set. Or you can also just write the two curly brackets with nothing in between. So we'll use the curly brackets to talk about sets. If you just write the curly brackets with nothing in between, then that will represent the empty set. Or what you see here is called set builder notation. And you would read this as the collection of X, that's what this means. And then you have this straight line here, that means such that. So we have so far the collection of X such that, and then the information here on the right side of the bar tells us which members we're going to admit to our collection. In this case, X that are not equal to themselves. So that's kind of a contradictory statement, so you can see why this set will have no members. And then the note here says, like the number 0, this set plays a vital role in mathematics. So you might be thinking, why on earth would we care about a set that has no members? In terms of sets, it kind of plays the role of the number 0. Okay, and then the next set that we might encounter is the set of natural numbers, sometimes called counting numbers. So the ellipses here indicate that this counting keeps going. So the set of natural numbers begins with 1. It does not include 0 or any negative whole numbers. And it's 1, 2, 3, 4, and so on. So any number, any whole number that you can think of, like maybe 19 or 1,000 or 1,000,000, they all belong to this set, and that's what this ... means. If we include the 0, then we can call these whole numbers. So if we just have 1, 2, 3, and all the numbers past that, all of the integers past that, then we call them the natural numbers. If we throw in 0, we call it the whole numbers. So I use the word integer without telling you what an integer is. So if we expand our collection a little bit, now we want to include -1, -2, -3, etc., then these are called integers. So again, -19 is in this set, and -1,000,000 is in this set. And let me scroll back up for just a moment, and notice here this script n that we use to represent the natural numbers, and the script z that we use to represent the integers. So you can use this notation in our class. You'll just write n with an extra line here on the side, or z with an extra line there. And that's going to indicate the natural numbers and the integers respectively. Similarly, We denote what are called the rational numbers by this script Q. You can also use this symbol. So what is a natural number? Rather, a rational number? Well, it's got the word ratio here in the name, right? And a ratio, we know, that talks about fractions. So precisely, we describe the set of rational numbers as the set of ratios or fractions, a over b, where a is an integer and b is an integer. So this symbol means belongs to. So again, the set builder notation would be read: the set of rational numbers is equal to the collection of all a over b such that a belongs to the set of integers and b belongs to the set of integers. Now, we want to make sure that this b on the bottom is not 0 because we don't know how to divide by 0, and that will be an issue that we'll face in our class going forward. So it turns out that another way to describe this in set builder notation would be to say that Q, the set of rational numbers, is equal to the collection of all x such that x possesses a repeating or terminating decimal representation. So for example, we know that 1/4 is a rational number. It's a ratio of integers, and we can express 1/4 as 0.25. So this is what we mean when we say terminating decimal. I could write 0.25000, but I don't need to. Or we have rational numbers like 1/3, which is equal to 0.3333, and that goes on forever. That's what's called repeating decimal representation. So any number that can be expressed as a decimal with either a finite length before it's 0 afterward, as in the case of 1/4, or maybe it has an infinite representation like 1/3, but there's some pattern there in that decimal, then we call that repeating or terminating decimal representation. And it turns out that every rational number is going to possess this property, and exactly the numbers that possess this property are the rational numbers. Now, another fun one before we move on is 1/7. So 1/7, if we write the decimal expansion, would be 0.142857, 142857. So this might look like a big mess of numbers, but we can observe that there is actually a repeating pattern here. It's not quite as nice as 1/3, which repeats every space, but it does repeat, and this will go on forever and ever, 142857. So 1/7 is, of course, a rational number, but we knew that because it's the ratio of two integers, 1 and 7. Okay, next, the real numbers. So the real numbers will be the collection of all numbers x that possess a decimal representation. So just to give you an example of a number that is real, but maybe not rational, say the square root of 2. We don't know how to express this idea, the square root of 2, in terms of a ratio of integers, but it does have a decimal expansion, and so it is a real number. Another real number that we don't know how to express as a rational number would be something like pi. You might be familiar with pi. And you don't have to know much about pi for this course, but we just want to know that this is a real number. And so it does have a decimal representation. Then we have the irrational numbers. Square root of 2 is one of those. So you'll notice we have rational numbers. Irrational numbers are real numbers which are not rational. And then finally we have the complex numbers, which will be numbers of the form a plus bi, where a and b are real numbers, and I is the square root of -1. So we will be working with complex numbers a little bit in this class. So you do want to know all of these different sets of numbers. And if we look back at our collections, we see that the set of natural numbers is a subset, or it's contained inside the set of whole numbers. And the set of whole numbers is contained in the set of integers, is contained inside the set of rational numbers. The set of rational numbers is contained inside the set of real numbers. And the set of real numbers is contained inside the set of complex numbers. So that's just a brief introduction to sets. We're going to be talking more about sets, as I said, as we learn to solve equations. We'll be talking about sets as sets of solutions of equations. We'll be talking about domain and range in terms of sets oftentimes. So these will come back, but for now, just learn these basic definitions. And let's talk a little bit about rules of exponents. So this should just be a little bit of review of how we manipulate exponents. So you can see we have the rule that if we multiply something that looks like a to the m by a to the n, this a is referred to as the base. And you notice here that the bases are the same. So we need to have the same base. If we have the same base and we multiply that base to two different powers, we add the powers. So multiplication becomes addition in the powers. Then it makes sense, since multiplication and division have this kind of inverse relationship, that division should be subtraction in the powers. The next rule says if we raise a base to a power and then raise that to another power, as in a to the m to the n, then that's going to be multiplication in the powers, a to the m times n. We also want to know that these exponents distribute across this product. This n here that I have in the power gets applied to a and b when a and b are multiplied. So a, b, everything to the power n is the same thing as saying a to the power n times b to the power n. And the same thing when we divide. This power n gets distributed to the a and to the b. So a over b, everything to the power n, is the same thing as a to the n over b to the n. Let's skip the power of a negative quotient for just 1 minute and look at negative exponents. So the negative exponents rule tells us that if we have a to the minus n, that's the same thing as 1 over a to the positive n. So we can think of a to the minus n as sitting over 1, and the fact that this exponent is negative, that means that I want to take the whole term and move it downstairs to the bottom of my fraction, and when I do, the power becomes positive. So a to the negative n is equal to 1 over a to the n. Similarly, if we had the negative power on the bottom, then this entire term a to the negative n gets to move upstairs, and it becomes a to the positive n. So when we move a term from the bottom of a fraction to the top, or from the top to the bottom, we change the sign of the power from positive to negative, and vice versa. So then if we go back and we look at the power of a negative quotient, the previous rule, and we think about what we know from the power of a quotient rule. So we're combining this power of a quotient rule with this negative exponents rule. First of all, we'll distribute this power to top and bottom, and that gives us a to the minus n over b to the minus n. And then we swap the places and we make these negative n's into positive n's. So it's b to the n over a to the n. Now finally, we know from our dividing rule way back up here that a to the m divided by a to the n means subtraction. So then if I look back down at the zero exponents rule, it tells me that a to the m divided by a to the m, that should be a to the m minus m, which becomes a to the 0. And anything other than 0 raised to the power 0 is 1. So we're going to remember that raising something to the power 0 is equal to 1, unless that thing is 0, then we have to be a little careful. But most of the time, we probably won't encounter that situation. Okay, so now we know our rules of exponents, and we're going to use these rules to rewrite each of these expressions in the simplest form. And it says using only positive exponents. So we know that if we have negative exponents, we're going to need to make them into positive exponents, but we have a rule for that. So the first example is x squared times x cubed times x. So I'll look again at my rules, and I see that this looks like the first rule, multiplying, and that tells me that I add the powers. So this should be equal to x to the power 2 plus 3. Well, I don't see a power here in the third term. When we don't write the power, that's to the power 1. So this becomes x to the power 2 plus 3 plus 1, which is x to the power 6. And I have a positive exponent, so I'm done. Now, notice that we had the same base here, x, x, and x, and that's why we could just write the base one time and add those powers. Let's look at example 2. This is also multiplication, but here I have these integers, 5 and negative 4. So the way this will work is I'm going to multiply them first. So this is 5 times negative 4, and then I have the base x raised to the power 3 times the base x raised to the power 2. So this is negative 20 x to the 3 plus 2, which is negative 20x to the power 5. So let's do the same thing here. Now I've got two different bases. I've got x's and I've got y's. So I want to make sure that I combine them in an orderly fashion. So I'm going to say, well, first I need to multiply negative 2 and negative 3, the integers out in front. Then I have x squared, x to the power 4, y cubed, y to the power 4. So this becomes 6. When I multiply a negative times a negative, it's positive. X to the power 6 because I'm adding 4 plus 2, y to the power 7 because I'm adding 3 plus 4. Same thing here. I have two bases, a and b. So I multiply negative 3 times 5, a to the power 4 times a to the power 9, b to the power 2 times b to the power 7, and this becomes minus 15, a to the power 13, 9 plus 4, and b to the power 9. Now so far, I have only had positive exponents, so I haven't had to worry about anything. But we might run into a situation later because the problem instructs us to use positive exponents where we'll have negative exponents. Let's see. So all of those were the multiplication rule where we got to add the powers. Now we have division, it looks like, which means that I subtract powers. So I know that my rule above tells me that if I have q to the power 7 over q to the power 3, that should be, they're the same base, q, so I'm going to say 7 minus 3. I also have minus 18 over minus 6, and that I can just cancel as usual, cancel the negatives, cancel the 6 goes into 18 3 times. So that 3 will stay on top. I have 3q to the power 7 over q to the power 3 is 3q to the 7 minus 3. That's 3q to the power 4. And again, my exponent is positive, so I don't have to go any further. Okay, and we can do this even if we have more than one base, as you see here. So again, with the integer terms, I'm just going to cancel them. I see that 9 goes into 36 4 times, so I'm going to say this is 4 on top. And then I have a to the power 3 minus 1, b to the power 8 minus 3. So that is 4a squared, b to the power 5. Then I have minus 120 over minus 15. 15 will go into 120 8 times. So this is going to be 8. Then I have r to the power 10 minus 2 and s to the power 7 minus 6. So that's 8r to the power 8s. And I can write s to the power 1, or I can just write s. Okay, now we're asked to simplify each expression, and we're going to assume that all of the bases are non-zero, because we know that anything other than 0, raise it to the power 0, gives me 1. But we don't know about 0. So 29 to the power 0 is 1. 13 to the power 0 is 1. Now I want to be a little careful here, because it might look like I have a minus times a minus, which would become positive, but one of these minuses, this one, is inside the parentheses, and it's getting raised to the power 0, and I know that anything that I raise to the power 0 is just 1. So this actually is minus. I keep this minus from right here, 1. So minus 1, because the 1 inside, the minus inside, just becomes 1, but I keep the negative that was outside. So we want to be careful there. So here's another example where what's inside the parentheses is becoming 1, but then it's getting multiplied by another number. So this is 2 times 1, which is 2. And similarly here we have negative 2 times 1, which is negative 2. Okay, now we want to simplify these expressions. And again, answer with positive exponents. So 2 over 3 to the power minus 3. Well, I know that my rule says that this minus 3 power will get distributed on top and on bottom. So that becomes 2 to the minus 3 over 3 to the minus 3. But am I done? Well, I'm not done because I need positive exponents. So what can I do? Well, these guys can trade places. So this will be equal to 3 to the power 3 over 2 to the power 3. And that would be perfectly fine. If you wanted to multiply this out, you could. We know 3 times 3 is 9, and 9 times 3 is 27. 2 times 2 is 4, and 4 times 2 is 8. All right. Now, I have negative of negative 3 to the power negative 4. So it's important to realize here that because of these parentheses, the base that I'm raising to the power is everything inside the parentheses. So negative 3 gets raised to the power negative 4. So I'm going to treat the minus sign that's in front separately, and that's going to stay here. And then I'm going to just work with what's inside the parentheses. So I see that I have a power of negative 4. So let's first write this as a fraction where we move this negative 3 to the bottom, and we say that that negative power becomes positive. Okay, that's good so far. So what is this really? Well, this is minus in front, 1. On the bottom, I have minus 3 times minus 3 times minus 3 times minus 3. Now here I know that minus times minus is plus, so this becomes 9. And minus times minus is plus, so this is 9. So on the bottom here, what I have is 9 times 9, and I still have the minus in front. So this is minus 1 over 81. And this minus should be right in front. Although it wouldn't matter if I wrote it on the top, that would still represent the same number. It's more proper to write this minus sign out in front. Okay, good. Our next example is y to the power negative 6 over y to the power 12. So we have division, and we know that our rule tells us then we subtract. So we have y to the power minus 6 subtract 12, which is y to the power minus 18. Now I can't stop there because I need to finish with a positive exponent. So I know that I have to move this to the bottom of a fraction, make it 1 over y to the power 18, and then I have a positive exponent, so that's going to be my final answer. Now I want to point out here, I could have said, well, this is equal to 1 over y to the power 12 minus 6. And that's equal 1 over y to the power 12 plus 6, which is 18. So we're going to get the answer either way. The first line that I wrote in blue, I applied the rule for dividing, and then I changed the negative exponent to positive. In the second line that I wrote in yellow, instead I first changed the negative to a positive, and then I used the addition rule of moving it downstairs. So either way is fine. So then notice here, I have x to the power minus 6 over y to the power minus 2. So now my bases are different. So I don't get to add the powers because the bases are different. The bases are negative, so I know that I want the power negative 6 to be positive 6. That means I'm going to move it to the bottom, so this becomes x to the positive 6. I want this negative 2, the power of y, to be positive, so I move it to the top. This is y to the power positive 2. Okay, a few more examples. Here you can see we're doing multiplication again. So as above, we're first going to multiply any integers or number coefficients that we have. We have negative 4. And then I have a to the power 7 and a to the power 10, so that becomes a to the power 17. Then I have b to the power minus 12, b to the power positive 2. So minus 12 plus 2 is 10, negative 10. So this is minus 4, a to the 17, b to the negative 10. And because I always want to finish with positive exponents, I know that I have to make this minus 4a to the 17 over b to the positive 10. Next, minus r to the power 4t to the power minus 9 times minus 6r to the power minus 7t to the power minus 1. So first I can multiply minus 6 and negative 1 to get positive 6. Then I have r to the power 4 plus minus 7 t to the power minus 9 plus minus 1. Notice how I'm using parentheses here around the minus signs so that I don't get myself confused. So this is 6r to the negative 3, t to the negative 10. And I know that I want positive exponents only, so I'm going to say this is 6 over r cubed t to the power 10. And just move those to the bottom of the fraction. All right. Let's do another example like this. I have negative 3 times negative 1, so that's positive 3. P to the minus 5, not 15, 5. P to the minus 5 plus minus 12. I'm just going to write minus 12, even though it's plus minus 12. Q minus 11 plus 6. That's 3 p to the minus 17, q to the minus 5. So I move them downstairs, keep the 3 up top, p to the 17, q to the 5. All right. 5 times 2 is 10. M to the power 5 plus minus 2. N to the power 8 plus minus 7 is 10m cubed n. Then we have 5 times 4 is 20. 20 y to the power 6 plus minus 5. Z to the power 2 plus 7. So 20y, z to the power 9. And it's perfectly fine to write just y. I don't have to write y to the power 1. In example 6, I have negative here in the second thing that's being multiplied. So negative 1 times 4 is negative 4. Then I have m to the power minus 8 plus 2. N to the power minus 6 plus 6. So that's minus 4 m to the power minus 6, n to the power 0. I know that I want positive exponents, so I'm going to say this is minus 4 over m to the power 6, and n to the power 0 is just 1. So I don't have to write times 1, because anything times 1 is just that thing. All right. In example 7, minus and minus will cancel. 24 is divisible by 2, so I have 12 here, and 14 is divisible by 2. That becomes 7 on top. So if I've simplified my coefficients, I have 7 on top and 12 on bottom. Then I have m to the power, I could do 3 minus 12, or I could do 12 minus 3. So the smarter thing, I think, would be to do 12 minus 3, because then I know that I'll end up with a positive exponent, which is what I want in the end. And I have n to the power 7 minus 12, so plus 12. Again, I'm choosing to move to the bottom because I know that in that way I'll end up with the positive exponent that I want. If instead I moved them to the top, that would be fine. That's not wrong. We just have to do one more step, because we'll end up with a negative exponent. We move them to the bottom in the end. So this becomes 7 over 12 m to the power 9, n to the power 19. So negative 16 and negative 20 have a common factor of negative 4. So if I remove that factor or cancel it out, I have 4 on top, 5 on bottom. Then I have f to the power minus 5 over f to the power minus 3. So I'm going to make this minus 3 plus 5. I changed this minus 5 to positive and moved it downstairs. Then I have g to the power 12 on top, minus 6 on bottom. So I'm going to make this g to the power 12 minus or plus 6. When I move this minus 6 to the top, it becomes positive. So this becomes 4g to the power 18 over 5f squared. So again, as I said, it's not a problem if you do it the other way. Let's just see that one time. So instead, if we had canceled the coefficients and had 4 over 5, and we had done f to the power minus 5 minus 3, and g to the power 12 minus 6, then we would get 4f to the power minus 2, because minus 5 plus 3, and g to the power 18. And I would just have, that's all over 5, I would just have one more step to do in order to move this f to the power minus 2 down. So since we're new at this, if you want to do that extra step each time, I would recommend that. That way you make sure you get it right. And then once you're a little more comfortable, you can start doing it just in one step. So it does look like that's the end of the examples for this lecture. So we'll stop here, and then we'll do the next lecture in a separate video.